This is part 2 of section 6.2, dealing with separable equations. I'll be dealing with a little more complex differential equations. Still using the same technique as far as how to solve it, and we'll bring up something that I think you guys might find somewhat interesting and might leave you guys somewhat perplexed. So the differential equation is given to us as 2x times 1. So I still want to use the same technique, which is collect all the x with the dx's, all the y's with the dy's, and integrate both sides. Alright, so I have a dy dx equal to 2x multiplied by y. This dx gets multiplied over here, so it's dy equal to 2x y dx. To get y on this side, I have to divide by y. So you can think of this as dividing both sides by y, and then the y's would cancel out. Okay, so I end up with the integral over here on the left is going to be, or my term over here on the left is y over dy, or dy over y, whatever I said, 2x dx on this side. At this point, I want to go ahead and integrate both sides. Alright, so this over here integrates like that, this over here integrates like that. Over here on the right side, the integral of 2x is going to be 2x squared over 2 plus c. I'm going to be able to reduce the 2's, so you can think of this as just basically x squared plus c. Over here on the left, you can think of this integral, if I have y in the denominator, it's going to be y to the negative 1 dy, and the integral of y to the negative 1 is going to be the ln, so it's going to be ln absolute value of y. Right? Now, I can easily solve this for y by taking e to both sides. Okay, so take e to both sides. Alright, so the exponential cancels off over here. So I end up with the absolute value of y equal to e to the x squared plus c. Okay. Now here's something that I came across with many times in my studies of calculus, and I would always get this wrong. Alright, so I developed something called the damn constant rule. Okay, so the damn constant rule is what this is. Alright, so let's say you have e to the x plus c, much like we have, let's say over here, but this is x squared, but it applies to any exponent. If you're adding inside the exponents, okay, sort of like if you're adding, like let's say x to the 3 plus 4, the exponent property basically says that if this is true if you're multiplying with the same base, right? If you're multiplying with the same base, you would add exponents. So really you're saying e to the x times e to the c, right? Well, c was a constant, right? So if you raise an exponential base to a constant, this is also going to be a constant. So e to the c is a constant. It's an arbitrary constant, right? So we're just going to call this, because you're multiplying by it, c times e to the x. And that's the damn constant rule, is the x plus c in the exponent, because you're multiplying, and this is a constant, just turns into a c in the front. So maybe I'll have to explain this again in class tomorrow, but this e to the c just turns into a big C in front of your e to the x. So this one over here turns out to be absolute value of y equal to a c e to the x squared. And the reason I call it the damn constant rule is when I was first learning calculus, I'd always forget this because this rule doesn't really have a name necessarily. So I'll forget to put the big C in front, and I'd get the answer wrong. I'd get docked off points. Now I always say the damn constant, always messes me up. So I just came up with my own little way of remembering it. It's a damn constant rule. So that's not really what it's called. It doesn't really have a name, but I just gave it a name. It helped me remember it, and hopefully, it helps you remember to bring the damn constant in front. Okay, so this is our solution. Now, if I want to get rid of these absolute value bars in front of the y, or what the y is in, what the absolute value prevents is it could either be positive or negative, right? So if I drop the absolute value bars, I'm going to say that C is going to be either positive or negative. So my solution is plus or minus C e to the x squared, right? And what this is saying is, like, if you think of it on a grid, if it's a positive C, it's going to be exponential growth going something like this. If you have positive C e to the x squared. But if you're allowing C to be negative, it's going to have basically the same shape, only it's going to be a flip on this side. So it's going to be something like this. So this is considering the case if it's negative, it's going to look something like that. Alright, so it could be that it's positive going like this, going up, or negative going down. That's why it's plus or minus. And this is the general solution to our differential equation way back over here. Okay. So I'll let that, maybe you can pause it at this point, let it kind of sink in. Maybe you have me re-explain what went on over here for it to make a little bit more sense. Okay, so this is our general solution. Alright, so there's one more example to get through. This example is I want to let y equal, or dy dx equal to 4 plus y. And I want to find a particular solution through this point. Right? So I set up my dy dx equal to 4 plus y. I want to cross multiply. So when I cross multiply, it's going to be a dy equal to 4 plus y parentheses dx. The reason I put parentheses, because I'm multiplying all of this by dx. And notice none of these terms have an x in them. So I'm going to have to divide this whole thing, 4 plus y, over here on this side. Alright. So my term over here is dy equal to 4 plus y equal to dx. Okay. Now the technique is to integrate both sides. So you may be thinking, well, what's the integral of dx? Well, if you kind of think of it as a little invisible 1, the integral of 1 is just basically x plus c. Over here on this side, I can do a little u sub. Okay, I'm going to let u equal 4 plus y. Du is just going to be dy. So this would be the integral of 1 over u, which is ln absolute value of u. Okay. So the integral over here is going to be ln absolute value of 4 plus y. And so continuing this way, if I were to take e to both sides, the e and the ln are opposites or inverses, so they cancel out. So I would end up with absolute value of 4 plus y equal to, I have e to the x plus c. The damn constant rule says it's going to be a c e to the x, and its absolute value of 4 plus y. Okay. Now, I wanted to find the particular solution that passed through this point, so I'm going to go ahead and apply my initial condition. My initial condition was 0, 3. This is my x value, this is my y value. So it's going to be absolute value of 4 plus 3 is equal to a c e to the 0, which just gives me a 7 equal to a c times 1. So my c value is equal to 7. So now that I know my c value is positive 7, I would let 4 plus y equal to a 7 e to the x. Now you may be asking, well, why did I drop the absolute value bars, from here to here? And because I've already solved for my c value, I don't have to worry about this piece being negative. So I don't really need to ensure that it's positive. It's already solved for. So now I can just drop the absolute value bars. Last thing I can do is subtract the 4 over. So my particular solution is going to be 7 e to the x minus 4. And that'll satisfy the differential equation as well as pass through the point 0 and 3. And that's it for this video.